Get started. We have almost achieved our goal of deriving the Schwarzschild solution. There's still a last step missing, which I will do now. We have reduced the metric to this form, where you have a function of r here only in front of dt squared. And we have the same function lambda in the exponent of the dr squared. And the angular element, d phi squared, plus d theta squared. And we had our system of 4 differential equations for the coefficients, now reduced to 2 differential equations for the lambda. Well, originally we had S1, S2, S3, S4. 2 of them are now automatically satisfied, and only 2 are left, and that's what we have to solve today, which will be not too difficult. So S2, no, that's the wrong page. Oops, yeah. S2 is a second order differential equation for lambda. It's minus d2 lambda dr squared plus d lambda by dr squared minus 2 over r d lambda by dr is 0. And S4 is a first order differential equation. It's lambda plus r e to the minus lambda d lambda by dr is equal to 0. So which one would you try to solve first? The second order equation or the first order equation? Well, I have a strong preference for beginning with the first order equation, because this involves only one constant of integration, right? And it's certainly quicker to do this. And then we can insert the result of the solution of this here into the second order equation and see if they are compatible. So I will begin with S4. And S4 is actually easy to solve with a substitution. And the substitution is that we write u or some other new symbol for e to the minus lambda. So we write u of r is e to the minus lambda of r. Then, of course, we get du by dr is e to the minus lambda, which is u, or I may write e to the minus lambda. And then with a minus sign, the derivative of lambda, right? That's precisely the expression we have here. So you see that that's a convenient substitution. And then our differential equation becomes 1 minus e to the minus lambda is u plus r. E to the minus lambda d lambda by dr is minus du by dr. So the plus becomes a minus du by dr, and the whole thing is 0. Of course, yeah, how would you solve this system of differential equation? By which method? Well, the standard method. That's the first method you should always try if you have a first order differential equation. It goes under the name separation of variables. Try to get all terms which involve one variable on one side and all terms which involve the other one on the other side. And that's easy here, right? So, okay, let me do it in 2 steps. So first I could solve for du by dr. Then I have 1 over r. This is now on the other side, so I have 1 minus u here. And now it's easy to separate the variables. So I have du divided by 1 minus u is dr divided by r, right? And it's easy to integrate. So this gives a log, right, with a minus sign. That's minus ln 1 minus u. If I differentiate this, differentiating the log gives 1 over 1 minus u, and this minus sign kills this minus sign, so I get indeed 1 minus u. And on the right-hand side, I get ln r. And of course, I get an integration constant. And well, it's convenient to write this on the right-hand side in this form. I call the integration constant rs. And obviously, it should have the same dimension as r. So it should have the dimension of a length, right? So that's our solution. And then I can exponentiate this. Let me put it here. And then I get, if I exponentiate both sides, I get e to the minus log. That's 1 over, right? So this is 1 over 1 minus u is r over rs. Yeah, if I exponentiate both sides. Okay, can I solve this for you? I think I can. This is rs over r is 1 minus u. And this implies that u, and u was nothing else but e to the minus lambda, our unknown function. U is 1 minus rs over r. So that's the general solution to S4. So it involves one integration constant. About the physical meaning of the integration constant, we have to talk in a minute. It has a dimension of a length. That's the only thing we know at the moment. So we have to check what about S2. And I claim that S2 gives no further information, that it is automatically satisfied. So that we have found already the general solution to the whole system of equations. Let's check this. So if e to the minus lambda is this here, then lambda is minus the log of 1 minus rs over r, right? So we can calculate what d lambda by dr is. I have a minus sign. If I differentiate the log, I get 1 over. And if I differentiate this here, I get minus minus, so the sign remains unchanged, rs over r squared, which I may also write as rs over r squared minus rsr, which is more convenient for differentiating, because we also need the second derivative. So let's calculate the second derivative. This is, I think I've forgotten the minus sign, right? There was a minus sign. No? I think it should be a minus sign. So I differentiate this now. I have minus and another minus because I differentiate an inverse function. So I get plus rs over r squared minus rsr squared. And then the inner derivative, if I differentiate this here, I get 2r minus rs. And what I have to check is whether this expression is really 0. That's minus d2 lambda over r squared plus d lambda dr squared minus 2r d lambda dr. So let's just insert what we have found. Minus this here, minus rs 2r minus rs over r squared minus rsr squared. That's this here, the first term. Then this term, that's this here squared. So the minus sign is killed if I square, and I have r squared minus rs r squared. And the last term is minus 2 over r, and then the first derivative, which is another gives another minus sign. So I have plus rs, and here r squared minus rsr. So I would like to write everything over the same denominator. So I multiply this with the appropriate factor here. And then I have the same denominator in all terms, right? Well, almost. I have to multiply this here with r. So I get, oops. So I write everything on the denominator. This here. So I have to multiply this here with r. Then I get minus 2r squared rs. I get minus, and minus gives plus rs squared r. I have to multiply this with r, so I get r rs squared with a plus. And here I get plus 2 rs r squared minus 2 rs squared r. Let's see, that's the same as this. And these two together are the same as this. So I get indeed 0. Yeah? So everything is fine. So we have solved our system of equations. We have found the most general solution. So we have found the Schwarzschild metric. So the Schwarzschild solution. What? It is G. Well, we had e to the minus lambda. I now write this solution, 1 minus rs over r. So I get minus 1 minus rs over r dt squared plus dr squared. Here I have e to the plus lambda, so that's the inverse of this here. So I have this in the denominator and the angular part, with which we didn't do anything during the whole calculation. It always remained what it was in the beginning. And that's the Schwarzschild solution. So that's the metric which Karl Schwarzschild found in 1916 as a solution for a spherically symmetric space-time. So whenever you have a spherically symmetric solution of the vacuum equation, whenever you have a spherically symmetric solution of the vacuum equation, it must be of this form. So this is a region outside of a star. That's the most interesting case. It would also apply to a shell, for instance. If you have a vacuum shell between two massive shells, then in the shell also this form of the metric must be valid. So the only thing we have used is spherical symmetry and the vacuum field equation. So every such situation is covered by this metric. Okay, two questions arise. Well, first question, we have done a lot of coordinate transformation. You might ask, what's the geometric meaning of this coordinate r with which we actually end up? You might be tempted to interpret the r as a distance of from a certain center. But that's not the right interpretation. You can read it from this term. If you consider a radial line, then only the r changes along this curve. This is 0, this is 0, this is 0. Yeah? You have constant t, constant theta, constant phi. You just move along the r line. So then you would have to evaluate this term. And this tells you that the length along this radial line is not given just by the value of the r coordinate. It's modified by this term. So the length of a segment would not just be r2 minus r1. Yeah, if this is r2 and this is r1. So r should not be interpreted as a distance from something. That's a wrong interpretation. The right interpretation can be read from this term. If you consider a circle, then only phi varies. So this is 0, this is 0, this is 0. Then only this term would be relevant. And if you do it in the equatorial plane, where theta is pi half, then this would be 1. Then you would have only r squared d phi squared. So the interpretation of the coordinate r is the following. Circle in the equatorial plane. So this would mean t equal constant, r equal constant, theta equal constant, namely pi half, because I am in the equatorial plane. And phi varies, between 0 and 2 pi, right? So that would give us a circle in the equatorial plane, and we can calculate from this formula the circumference of this circle. Well, what is it? Let's call this circumference u. So this would be the integral over the circle, where I have to write g mu nu or let me write by ds, dx mu by ds, dx mu by ds, ds, right? That would be the circumference of the circle. I have to measure the length with my metric. So this is a length element measured with a metric. And I insert my metric. So the only coordinate which varies is a phi. So I only have a phi integration here. So I have g phi phi d phi by ds, d phi by ds. All the other terms are 0, right? Because the r by ds is 0 because r doesn't vary along the curve and so on. By ds over the circle. And g phi phi can be written from the expression here. So first of all, I can write this. Allow me to do it in this way. What we actually do is a substitution of the integration variable, right? But that's the usual shorthand notation for doing this. Then I have the square root of g phi phi is r squared d phi. And phi runs from 0 to 2 pi. So what we get is 2 pi r. Yeah? So a circle of radius r in the equatorial plane has circumference 2 pi r. And that's the geometrical meaning of this coordinate r. So in a sense, it's a measurable quantity. So you may think of lying out a rope along the circle of radius r. And then the length of this rope is 2 pi r. It's given by the coordinate r. That's the geometric meaning. So it's not the distance from a center. It's a measure for the circumference of circles. That was the first remark. Second remark. There's a constant Rs. So actually, the Schwarzschild solution is not just one solution, it's a one-parameter family of solutions. Yeah, and the Rs is a parameter. The question is, what's the physical meaning of this parameter? Any suggestion? What physical content could be hidden in this quantity Rs? Well, the whole thing is the analog of the Newtonian potential. Yeah? But we could ask ourselves, in the Newtonian case, where I have just one potential, what is the constant which parameterizes this potential? Well, what was the Newtonian analog? The Newtonian analog was something like minus gm over r, right? There's also one constant in it, which is not a constant of nature, but you could just look up in a book, and that's the m, right? The mass. So of course you would expect the Rs should have something to do with the mass. Of course, if I have a body of another mass, then the metric outside would be another metric, right? It would be rescaled in a certain sense. So of course the solution should depend on the mass of the central body, and this must be hidden inside the Rs. And now we want to find out what's the precise connection between Rs and the mass m. And well, the idea is exactly what I've said already. We compare with the Newtonian case. Yeah. So what's the meaning of? What is the physical meaning, I mean? Well, we compare with the Newtonian limit. Remember, the Newtonian limit was based on 4 assumptions. I call them N1 to M4. And of course, we have to check if these assumptions here are satisfied. N1 was the assumption that the metric should be close to the Minkowski metric. Yeah? So the metric should differ but little from the space-time of special relativity. Now look at the metric. This is not true in general, but it is true if we are far away from the body, if the r is very big. Whatever the Rs is, it is some finite number. So if I choose my coordinate r big enough, then it is always very small. Yeah? So I can compare it and I can forget about it in comparison with the 1. I can neglect it in comparison to the 1. So for r big, this is approximately just the Minkowski metric. So the condition N1 is satisfied for big R. So if we consider the metric for big R, then we can use the equations of the Newtonian limit. So N1 is satisfied for big R. What about the other ones? N2 was the condition that the metric should be time independent, at least approximately. Well, here it is even precisely time independent. So this is always satisfied everywhere. And 3 was a condition that, well, this was about particle motion. It had nothing to do with the metric, that we considered particles which move slowly in the metric. So this gives no restriction on the metric. And N4 was a condition on the energy momentum tensor, that the matter moves slowly and that it can be approximated by a dust. Well, here it is vacuum. So it is certainly a dust which moves with any velocity, namely with a density 0, right? So N4 is also satisfied. So if we look at the metric for large values of R, then the equations of the Newtonian limit should apply. So we should be able to compare the equation with Newtonian equations. And this should tell us how the RS is related to the mass. So remember in which way the potential entered into the Newtonian limit. So for large R, we must have, well, this was a relation which connects the potential G naught naught. Yeah? So the coefficient of the x naught component, x naught is c times t. So this was minus and then 1 minus phi. No, I think I wrote a phi of this sort, phi over c squared. That was the equation which we derived, which must hold, that it must hold in the Newtonian limit. Sorry, almost this thing, plus 2, sorry. That was a correct equation. So that's the Newtonian potential, and that's coefficient in the metric in front of the x naught. So we can read the G naught naught from our equation. I forgot the c squared here. Nobody protested. Well, as I said repeatedly, I usually work with c equal 1, and that's the reason why I very frequently forget the c's. So there was a c here. So c times t is x naught. So this coefficient here, including the minus sign, that's G naught naught, right? So this is minus 1 minus Rs over R. And what was the Newtonian potential? So I have here 2 over c squared, and the Newtonian potential was minus Gm over R. Okay? And now we read what the Rs is. So these two terms must be the same. So I have an R here, I have an R here, so the Rs must be just this here. So the Rs must be 2Gm over c squared. That's what it is. So it is given by the m, right? So many books and many authors work with units where c is 1 and where g is 1. And then Rs is just 2m. That's the statement you will often hear, that Rs is just 2m, and Rs is a so-called Schwarzschild radius. So this is the Schwarzschild radius. It is just the mass of the body multiplied with constant of natures in an appropriate way so that it becomes the dimension of a length. So as a Newtonian problem, the general relativistic problem is parameterized with the mass of the central body. Yeah? And what enters into the metric is actually this combination, the mass multiplied with 2g over c squared. So then it becomes a length. And now if you look at the metric carefully, you see that there is a problem. Namely, you have this quantity here in the denominator. And if you have something in the denominator, you should make sure that it cannot become 0. Yeah? Because a 0 in the denominator is very bad. Now we have calculated that the Rs is positive. Of course, we want to have a positive mass, right? So the Rs is positive. And you see for a positive Rs, there's a positive value of R for which this becomes 0, namely if R is equal to Rs. Yeah? So, and that was a problem that puzzled people for several decades. Of course, it was immediately realized after Schwarzschild has found this solution that there is this singularity, and then people discussed this for decades. They had the wildest ideas what's the meaning of this, and it was clarified only in the 1950s, in the late 1950s, in particular by a paper of David Finkelstein. We will discuss this later, and this will lead us to the notion of a black hole. So the correct answer to this problem will be that if the situation is such that R can become equal to Rs, then we are in the situation that we have a black hole, and the Rs gives the horizon of this black hole. what do I mean by saying if we are in the situation where R can become equal to Rs? We should always keep in mind that this solution is valid only in the region outside of the star. The star has a radius, R star I called it, and the solution is valid only outside, not inside the star. So if the star is so big that the Rs is inside the star, then the singularity is completely irrelevant. Yeah? Because in the domain of validity of this expression, there is no singularity. This problem becomes relevant only if I compress a star to a radius smaller than Rs. And then indeed problems arise. But maybe it's a good idea first to check a few numerical values for celestial bodies to get an idea how big this Rs is, for instance, for the Sun and for the Earth. So that's easy. We could look up the G and the C in any table work, and we could look up the mass of the Sun, of the Earth, and whatever we are interested in, also in tables, and then we can calculate this length. And what we get is, in fact, we get surprisingly small radii. So for the Sun, we get Rs approximately 3 kilometers. And of course, the radius of the Sun is much, much bigger than 3 kilometers. Yeah? So this singularity is completely irrelevant for the Sun, because the solution is valid only outside the Sun, and there the R cannot become equal to Rs. For the Earth, we get something like a centimeter. So obviously the Sun is bigger than, the Earth is bigger than this. Was it a centimeter? I think so, something in this order. Yes, approximately a centimeter. But of course we can think of a hypothetical celestial body for which its actual radius is smaller than the Rs. And then we have to discuss what happens at R equal Rs. And this will then lead us to the notion of a black hole. So if you compress a body so strongly that its actual radius becomes smaller than this Schwarzschild radius, which is also called the gravitational radius sometimes, then actually it's no longer an ordinary star or something like that. It collapses into a black hole. That's what we will discuss fairly soon. But for the time being, we consider only bodies which are bigger than Rs, and then we have no problems with the singularity. So let me write here singularity. I put this in quotation marks because it's actually not a singularity in the sense as a word is usually used in general relativity. It's what is called a coordinate singularity. So I just mean a zero in the denominator, right? Singularity at R only relevant for bodies with R star. That was the symbol I used for the radius of the object, for the star, whatever it is, if this is smaller than Rs. And that's obviously not the case for the Sun and for the Earth. And we will discuss this later, next Wednesday, I think, when we talk about black holes, Schwarzschild black holes. Okay, so we have finally succeeded in deriving the Schwarzschild solution. We have got a rough understanding what the meaning of the R coordinate is, and we have got an understanding what the parameter Rs means, by which the Schwarzschild solution is parametrized. So at the end of this section, let me summarize. Summary of properties of the Schwarzschild metric. Oops, Schwarz. So an important thing which you should keep in mind is that it is time independent. Yeah? Actually, there are two different notions of being time independent in general relativity. We distinguish spacetimes which are static from spacetimes which are stationary. And the claim is that, this here is static. What precisely does this mean? Well, the difference between being static and being stationary has something to do with the fact that also a rotating object is in a sense time independent. Yeah, if it rotates with a constant, with a uniform velocity, then also the metric outside would be independent of the time t. But nonetheless, there would be a sort of motion, right? And the difference by which you see this is that the t lines, yeah, these are the integral curves of the distinguished observers, which are distinguished by the symmetry, that the t lines are twisted for a rotating object in space-time. Yeah, if the time goes upward, then the integral curves of the t lines are twisted for a rotating object, like spaghetti on a fork. Yeah? And by contrast, for a static space-time, this should not be the case. For a static space-time, there should really be nice straight lines, one next to the other. And mathematically, the difference is that in one case, you can introduce hypersurfaces, which are perpendicular to the t-lines, and in the other case, you cannot do this. And in fact, here you can do this. You can introduce hypersurfaces, and then you call the metric static. So let me write this down. So first of all, it admits a Killing vector field. We discussed this notion briefly on the last worksheet. The Killing vector field, namely that's the vector field d by dt. And Killing vector field for a vector field of this form simply means that, that the metric coefficients are independent of t. Yeah? If this is the case, if you can write a vector field as the basis vector field with respect to a certain coordinate, and if I find that this coordinate doesn't occur in the coefficients of the metric, then I call it a Killing vector field. By the way, this is named after a German mathematician, Wilhelm Killing. Has nothing to do with the English word to kill. Yeah? So that's a German name. So this is a Killing vector field. This means that the metric coefficients are independent of t. Look at the coefficients. They do not depend on t. No t dependence anywhere. And in addition, this is orthogonal to hypersurfaces, three-dimensional submanifolds, namely to the hypersurfaces t equal constant. Yeah? We have no cross terms here, where a dt is multiplied with a dr or with a d theta or with a d phi. This expresses the fact that the t lines are perpendicular to the surfaces t equal constant. So the t lines are perpendicular to hypersurfaces. It means they are not like spaghetti on a fork. Yeah? They are straight, one next to the other. So you can introduce these hypersurfaces perpendicular to them. And that's what we call static. Yeah? If only the first part would be satisfied, but if we could not introduce such hypersurfaces, then we would call the metric static. So for instance, if some of you have heard about the Kerr metric, which describes a rotating black hole, there we have also a time-like Killing, oh, I forgot to say, a time-like Killing field, of course. Yeah, so that I really can interpret integral curves as motions of observers. It must, of course, be a time-like Killing vector field. So in the Kerr metric, we also have a time-like Killing vector field, but it is not hypersurface orthogonal. And this tells us that we have a rotating object. Yeah? So the Kerr metric describes a spinning black hole, whereas the Schwarzschild spacetime describes an object which is not spinning, which is spherically symmetric. So that was the first important observation. We get a static metric. And this comes out automatically from the assumption of spherical symmetry and the field equation. So every spherically symmetric field equation, a solution of the vacuum field equation is static. That's the Birkhoff theorem. Second observation, it is what is called asymptotically flat. This means it approaches the Minkowski spacetime, or the Minkowski metric, spacetime of special relativity for r to infinity. Yeah? We already used this when we discussed the Newtonian limit. So if you have a big radius value r, if the coordinate r is big, then we can neglect these terms in comparison to the one, and then we have just the Minkowski metric. So far away from our central body, we have the same physics as in Minkowski space. We have flat space. The gravitational field vanishes asymptotically. That's what it says. And the third property, that's what we put in from the beginning. It is spherically symmetric. And well, I just introduced this by deforming the Minkowski metric in a way that it remained spherically symmetric, so that we just, by looking at it, found out that no directions were distinguished from other directions. But you can do this in a more sophisticated mathematical language using this notion of killing vector fields. Also, spherical symmetry is associated with killing vector fields. In this case, not time-like killing vector field, but rather space-like killing vector fields which generate rotations. And we can do this for any spatial axis. And because there are three linearly independent axes, we get three linearly independent killing vector fields. There are three linearly independent killing vector fields generating rotations. So the integral curves of these vector fields are just circles. Yeah? So if I go along these integral curves, I'm rotating around my chosen axis. So these killing vector fields have a somewhat complicated form if I write them down in these coordinates. But for one axis, it's very simple to write it down. That's the axis which is distinguished by our choice of coordinates, not by the spacetime, but by our choice of coordinates. That's the z-axis. Our coordinates are adapted to the z-axis. And the rotation to the about the z-axis is just the rotation along the phi lines. Yeah? The integral curves of this vector field are just the phi lines. So for the z-axis, this is just the vector field d by d phi. Yeah? That's also a killing vector field. As you can easily see, none of the coefficients depends on phi. There is a coefficient which depends on theta, right? So d by d theta is not a killing vector field. Remember, the theta coordinate is defined in a completely different way as a phi coordinate. Yeah, it doesn't go from 0 to 2 pi along a closed circle. It goes in this way. So d by d theta is definitely not the killing vector field, but d by d phi is. And well, if you are interested in the other ones about any other axis, you can just make a coordinate transformation where the new axis, where your desired axis becomes the z-axis, and then you see how the vector field transforms. So these are three important properties, or mathematical properties, so to speak, of the Schwarzschild solution. Okay, we have now derived it, and now we want to fill it with physics. And, well, how do you do this? If you have derived a certain space-time model, which you assume is a good physical model for a certain part of our universe, in this case, for the neighborhood of a star or of any other spherically symmetric celestial body, how do you check if it's really a good model, if nature really behaves like this, where the most important tool you have is you consider particles and light rays, how they move in the space-time. And you check with nature if they really behave in the way the theory predicts. So what we will do now is we will study the motion of particles and of light rays in the space-time. And we will compare with actual observations in the solar system, in the gravitational field of the sun. So I begin with light propagation. So I begin with a light like geodesics. So that would be section 6.2. Well, mathematically, this would be about light like geodesics in Schwarzschild space-time. And after that, we talk about time-like geodesics, which will give the motion of freely falling particles. So light-like geodesics, you can think of light-like geodesics as being word lines of classical photons, and they tell us how light moves in this space-time. So what we will derive now, in particular, is the famous light deflection formula in the gravitational field of the sun. And then in the next section, when we talk about freely falling particles, then we will derive the perihelion precession of Mercury, among other things, which was also a big triumph of general relativity, that it could explain this. So let's talk about light-like geodesics in Schwarzschild space-time. So we have the metric, here it is, and what we have to write down is a geodesic equation. And the easiest way to do this is to use a Lagrange formalism. Yeah, so write down the Lagrange function for the geodesics and then discuss the solutions. Now we can make use of the symmetry because we have spherical symmetry. This means if I consider a particular photon, a particular light-like geodesic, this starts here with a certain initial velocity. Yeah? It starts here with this initial vector. Now this point and this vector together determine a plane through the center of our coordinate system. And because of spherical symmetry, the geodesic cannot deviate from this plane, neither in this direction nor in this direction, because the whole thing is mirror symmetric to this plane, right? So if it starts tangential to this plane, it will remain in this plane forever. So it suffices to consider motion in a plane. Yeah, we can restrict to a plane. And of course, we can choose our coordinate system such that this is the equatorial plane, theta equal pi half. So I will discuss consider light-like geodesics in the equatorial plane. No, this is spelled in this form. Equatorial plane. Equatorial plane means theta is pi half. And we do this in the Lagrange formalism. Okay, so what was the Lagrange function? Hope you remember. The Lagrange function, this depends on x and x dot. Dot means derivative with respect to s, the curve parameter, not with respect to t, our time coordinate. And the general form of the Lagrangian was 1/2 g mu nu, which depends on x mu dot, x nu dot. And the g mu nu's are now known. We have derived the metric, so we can write this for our Schwarzschild metric. What do we get? We get minus c squared, 1 minus s over r t dot squared, then plus r dot squared divided by 1 minus rs over r. And now I am in the equatorial plane. This means theta dot is 0. Yeah? There's no variation with respect to theta. And sine theta is 1. So I only get r squared phi dot squared. So that's our Lagrangian. So we have 3 Euler-Lagrange equations, the t component, the r component, and the phi component. Actually, I will write down only the t component and the phi component, because I will not need the r component in order to determine the path of the light rays. So let's consider the t component of the Euler-Lagrange equation. Well, just to remind you, the general form of the Euler-Lagrange equation was d by ds dl by dx mu dot minus dl by dx mu is 0. And now I do this for x mu equal t. So I get d by ds of what? I have to differentiate my Lagrange function with respect to t dot. Here's a t dot. The 2 kills the 1/2, and I get minus c squared 1 minus rs over r t dot. And dl by dt, well, L doesn't depend on t. That was the observation that d by dt is a Killing vector field, right? So there's no dependence on t. So for x mu equal t, this expression gives 0. So that's it. And what we have found here is a constant of motion. Well, c is a constant anyway, so I can drop this. So this expression here must be constant along my solution curve. It must be what is called a constant of motion. And that's what one usually calls E, because it can be interpreted as a sort of energy. Well, actually, it is dimensionless. So it is the energy in units of the rest energy of the particle. Yeah, you see, this is dimensionless. The curve parameter should have the same dimension as a as a t, and yeah, then this would be a dimensionless quantity. But it's a measure for the energy of the well, in this case we have a photon. So this interpretation as an energy is actually more relevant for the massive particle case, which we will treat afterwards. But also here I use the symbol E. And then we have the phi component. So that's our first equation, which we have got. Let's call it G1. Yeah? When I say it's constant, of course, I mean it is constant along one particular geodesic. Yeah? If I proceed along my parameter S along a geodesic, then it is constant. Of course, it's not a universal constant. Different geodesics have different values for E, of course. Yeah? So it's a constant of motion. Then we have to calculate the phi component. So this would be d by ds of, so I have to insert for x mu phi. So I have to differentiate with respect to phi dot. This gives this last term. So then I get, again, the 2 kills the 1/2, and I have r squared phi dot. And dl by d phi is again 0, because I have no phi dependence here. Also d by d phi is a killing vector field. So I found the second constant of motion, and this has something to do with angular momentum. So I call it L. And this is my equation, G2. Now I need a third equation. Yeah, I have 3 coordinates, t, r, and phi. So I would need 3 equations in order to fix the geodesics. So the obvious idea would be to calculate the r component. But it's actually more convenient to use the fact that the particle is a photon. So what does this mean for the Lagrangian, for this function L, for this expression here, that we have a photon, a massless particle? It must be something proportional to minus c squared, or actually exactly minus c squared, if I have a massive particle. That would be a time-like condition. But now we are talking about massless. Then it must be 0, yes. So that's exactly the thing which distinguishes massive particles from light rays. So this here, without the 1/2, would be minus c squared for massive particles if you use proper time parametrization. And it would be 0 for photons. So the condition, so for photons, for light-like geodesics, I must have as my third equation that this is 0. So this gives me this expression here. So I have minus c squared 1 minus rs over r t dot squared plus r dot squared over 1 minus rs over r plus r squared phi dot squared. And that's my equation, G3. So as I have already 3 equations, so it must be the case that the r component of the Euler-Lagrange equation doesn't give me any additional information, and you may check that this is indeed true. So you may use it, of course, it is valid, but it will not give you any additional information. So that's the 3 equations which we will use in the following. So our goal is now to calculate the path of the light ray. So we want to calculate the relation between r and phi. Yeah, r and phi are the polar coordinates in the plane. And we want to calculate the path of the particle, the photon in this case, in this equatorial plane in terms of the coordinates r and phi. So we need to know what have r and phi to do with each other. So obviously we can deduce from these 3 equations some information about dr by d phi. And that's what we want to do now. So we have an r dot and we have a phi dot floating around. And we will try to separate some information about r dot over phi dot. Yeah, this would be dr by d phi. That would give us the shape of the orbit. Oops. So where do I have? Here I have nice expressions which involves an r dot squared. So I can divide this by phi dot squared. Then I get here something which involves dr over d phi squared, right? So I divide g3 by phi dot squared. And I get 0 is what? 0 is minus c squared, 1 minus rs over r, t dot squared over phi dot squared. Oops. Then I have plus 1 over 1 minus rs over r dot squared over phi dot squared, plus r squared. So here I have the expression I would like to have. Yeah, that's dr over d phi squared. So I want to get rid of these two terms, and for this I use g1 and g2, because g1 and g2 allow me to express these terms in terms of the constants of motion. So I use now g1 and g2 in order to get rid of the t dot and the phi dot here. So I have 0 is minus c squared, 1 minus rs over r. And now t dot squared. What's t dot squared? I need g1. That's e squared over 1 minus rs over r squared. That's e squared over 1 minus rs over r squared. We write it on a line. So I've inserted t dot squared, and then I need a phi dot squared in the denominator, and that's L squared over r to the 4. L squared r to the 4. Then I have plus 1 over 1 minus rs over r, dr by d phi squared, plus r squared. Yeah? So here I use the chain rule. Yeah? So this is a usual shorthand way of applying the chain rule. So if I'm interested in r as a function of phi, that's the path of the particle in the plane which is coordinated by r and phi, right? Then this will give me the right information. So I want to solve this for this derivative, but first I observe that I can cancel one of these factors. Then I multiply everything with 1 minus rs over r, so then it becomes a bit nicer. And it's minus c squared e squared over L squared r to the 4 plus dr by d phi squared plus r squared times 1 minus rs over r. I think I can solve this for dr by d phi. So I get dr by d phi, or let's say the square of this. And I have, this becomes plus if I take it to the other side. That's c squared r to the 4 e squared over L squared minus r squared plus rsr. Okay? So this is, again, yeah, I could say it's a first order differential equation for dr by d phi, but in a very trivial way, it's already solved for the derivative. So I can write immediately d phi as what? It's dr, well, actually plus or minus. and then the square root of this thing here, right? The square root of c squared r4 e squared l squared minus r squared plus rs r. So that's the equation which gives me the shape of the orbit. And what we want to calculate is for a light ray coming in from infinity and going out to infinity, well, the geometry would be something like that. Here's my central body, which produces a gravitational field. My light ray now comes in, say asymptotically to this line. So it comes in here, goes through a minimum value of the radial coordinate, which I denote Rm. Yeah, so that's a minimum value of the radial coordinate along the path of the light ray, and then it goes back in this direction. So I would have here something like an asymptote. Yeah, it should be symmetric. What a nice drawing. So the cross section should be here, right? So it should be asymptotic to this here. So that's the situation I want to consider. So the light ray comes in from here or from here, whatever you like, and then goes through a minimum value Rm and then goes out to infinity. So altogether, it has a deflection angle. You see the deviation from pi of this, if I call this delta, then delta equals 0 would mean that the phi coordinate during the whole travel of the light ray goes over pi plus delta, right? What the phi coordinate sweeps out over this light ray is just pi plus delta. Yeah, that's the definition of the deflection angle. So if I want to apply this formula to this situation, then I would have to integrate on both sides. So the phi would go from 0 to pi plus delta on the left-hand side. And on the right-hand side, the r would go with an appropriately chosen sign from infinity to Rm, and then with an appropriately chosen sign from Rm to r. And obviously, both legs give a positive contribution to the d phi. The phi is always increasing. So the two things come with the same sign. So I can write that pi plus delta, that's the integration of the left-hand side, must be equal to 2 times the integral from Rm to infinity of the right-hand side of this expression there. Er root c squared r4 e squared over l squared minus r squared plus rs to r. Okay? So if I have the integral just once, then it gives the contribution which comes from this leg. But the contribution from the other leg by symmetry must give the same increase of the angle, because the situation is symmetric with respect to this axis, right? So the two integrals come with the same sign, of course, and therefore I can write just 2 times this integral. So that's the way in which you can calculate the angle delta for the Schwarzschild metric. And that's actually what an observer would see. This delta is the angle by which an observer would see a star misplaced in the sky, right? So think of an observer here at a large distance, somewhere here in this area, far away from the body. So he looks in this direction, and he sees the light ray coming from there, and he says, aha, the light is there, here, somewhere on this line. That's where he says the light must come from, right? But actually it comes from here. It is bent, and then it goes into the eye of the observer. So this angle delta tells exactly by which angular measure the star is displaced in the sky, right? And it appears displaced away from the center. That's the angle delta. And that's what Einstein calculated. Well, it was one of the first things he calculated from his theory. And well, as you certainly know, this was one of the first and most important tests of general relativity. We will talk about this in a minute. But first, let's do the calculation. So what we have here is actually an elliptic integral. Yeah? Actually, in this form, you cannot calculate it because you would need to know what's the relation between Rm and E over L. Yeah? So these things are, of course, not independent. If I have a fixed light ray, it comes with a fixed E and with a fixed L. And then the Rm is determined. So these two things are not independent of each other. So we have to calculate the relation between Rm and E over L. Then we can calculate this integral for any light ray we like. So that's what we have to do now. Relation between E over L and this minimum radius value Rm. Well, it's a minimum value. So the derivative, dr by d phi, must be 0 at this point. That's the condition which relates the two things. So I must get 0 if I consider dr by d phi at r equal Rm. And actually, it's convenient to calculate the square. If the thing itself is 0, then of course the square is also 0. And dr by d phi we have calculated here. It's here. It's exactly this expression. If I set r equal to Rm. So this is c squared E squared over L squared, and Rm to the fourth, minus Rm squared, plus Rs Rm. So I can solve this for E over L. No, actually for E squared over L squared. So I get Rm minus Rs over c squared Rm cubed, right? So I've cancelled one Rm. I've divided the whole thing by Rm. And then I have here Rm minus Rs and divided by this here. So I can insert this in my formula for the bending angle. And I get now the bending angle in terms of Rm only. So if I know the Rm, then I can use this formula. And it is what? It is this here, square root of c squared times r to the 4 times this here. C squared is cancelled, so I get r to the 4. Oh, what is this? Yeah, I think it's 2. Rm cubed, Rm minus Rs, and then the rest as it was, minus r squared plus rsr. So if you give me the Rm, if you tell me what's the minimum radius value of the light ray, I can calculate the bending angle with this formula. And what we have here on the right-hand side, that's what is called an elliptic integral. Yeah? So we have a fourth order polynomial of the integration variable r under the root. That's what is called an elliptic integral. Yeah, if you have a quadratic function, a second order polynomial, then you can solve it elementarily in terms of sine and cosine or things like that. If you have a cubic or a quartic polynomial, then you call it an elliptic integral. And you cannot express this in terms of elementary functions. But elliptic integrals are very well studied, and you know everything about them. So they are tabulated, they are implemented in any computer program you like, and you can easily evaluate this integral for any value of Rm you're interested in. Yeah? So you have perfect control over this expression. By the way, if you have a polynomial of higher degree than 4, then you call it a hyperelliptic integral. And they also occur in physics quite frequently. Actually, in our group, we have a couple of members who are very much specialized in working with hyperelliptic integrals because they occur very frequently in orbit equations. So here for the Schwarzschild orbit, you just get fairly harmless elliptic integrals. So we can evaluate this with any accuracy we like. But what is done in most textbooks is not that they work with this formula, that they are satisfied with a certain approximation. We may assume that we are fairly far away from the center, so far away from the center that we can linearize with respect to Rs over Rm. Yeah, Rs is a Schwarzschild radius. So for the sun, this would be something like 3 kilometers. Rm is the minimum radius value of the light ray. Of course, the light ray must be outside of the body, so this cannot be smaller than the radius of the star, which in the case of the sun is, I don't know, 10 to the 5 kilometers or something like that. Yeah? So it's much, much bigger than the Rs. So you can linearize this with respect to with respect to Rs over Rm, and then you get an approximation formula which is actually sufficient for many applications. And that's what Einstein calculated very early, in the very early state of general relativity, and that's the famous Einstein formula for the deflection angle. So in this case you get what? Well, in zeros order, so you expand this in a Taylor series, right? In a Taylor series with respect to this expression. And you consider only terms up to linear order. So you get a zeros order term and a linear term, and you forget about the rest. Yeah? The zeros order term, of course, gives you pi. It's not a surprise, right? Because if you have nobody at all, if the mass and thus the Rs is 0, then you should get no deflection at all. So you should get delta equals 0. Yeah? So that would be zeros order. And then comes the first order, and this comes out to be 2 times Rs over Rm. And then comes the higher order terms, which I not discuss here. And that is, this gives you delta is 2 Rs over Rm. And remember what Rs was? Rs was 2 times Gm over c squared. So I get 4 Gm over c squared Rm. And this is Einstein's, or that's not a precise formula, it's an approximation formula. Yeah? And that's Einstein's deflection formula. And actually this linearization, it can easily be done. I will not do it here on the board. So this will be one of the problems you could do on worksheet. What's the next one? 10 or 11? 11, I think, right? We have already done 10, I think, so it would be 11. So you can play around a little bit with these integrals, do a Taylor expansion, and then produce the Einstein formula. So what's the numerical value for the sun? Yeah. So I know G, I know M, I know c squared, and where the Rm cannot be smaller than the radius of the sun. So the biggest deflection I can get is the one which I get if I insert the radius of the sun here. That would be a light ray just grazing the surface of the sun. Yeah? So you can insert this, and you can calculate it, and you get this famous result of 1.75 arc seconds deflection. So for the sun, well, we can use this formula here. The sun, I already said Rs is approximately, or let's write for a light ray grazing the surface of the sun. Well, I would have to insert for Rm, for Rs, the Schwarzschild radius of the Sun, which is approximately 3 kilometers. And for Rm, the radius of the Sun, which is, 7 times 10 to the 5 kilometers, or something in this order of magnitude. Oops. Yes, 7 times 10 to the 5. Kilometers. So you see the quotient is very small, right? So we get delta is approximately 1.75 seconds of arc. You have an idea what this is? Any hobby astronomers in the audience? Have you seen Jupiter in a telescope? The disk of Jupiter in a telescope has a diameter of approximately 45 arc seconds. And it looks pretty small. Yeah, it's a small disk in the sort of telescopes you can use at observatories, which are open to the public. So this is a tiny, tiny fraction of this. But nonetheless, was easily detectable already 100 years ago, when Einstein established his theory, and when people tried to test it. And there was a famous expedition by Arthur Eddington, headed by Arthur Eddington. It was organized by the Royal Astronomical Society in London, and they verified the Einsteinian value, pretty well. Not with an overwhelming accuracy, but the order of magnitude was certainly verified very well. So this was verified by Sir Stanley Eddington in 1919 during a solar eclipse. At this time, one had to wait for a solar eclipse in order to observe starlight, which comes very close to the sun, right? So you have to observe in broad daylight, otherwise the sun is below the horizon. And if you do it with an optical telescope, then you have to wait for a solar eclipse, because otherwise you couldn't see stars in the immediate neighborhood of the sun. So what they did was they took a photograph of the neighborhood of the sun during a solar eclipse and compared with photographs of the same area of the sky which were taken half a year earlier. And they saw the stars displaced in the radial outward direction, at least in the average, in approximately this, by approximately this amount. Later, radio astronomy came about. Then people didn't have to wait for a solar eclipse. They could observe the light deflection of radio rays at any time of the year they liked. And now this has been verified to a very high accuracy. So I think it was the last thing I've seen. In the 90s, there was a radio astronomical measurement which got something like 0.04% accuracy. So it's established very, very well now. And actually now this is used not for testing relativity, it is used for getting some information about the solar corona. So any deviation from this formula one finds is interpreted as being produced by a matter effect of the solar corona. And you get information about the density in the solar corona by doing observations of this sort. So this is an important tool now for solar physics, actually. Nobody doubts that the deflection angle is correctly described by general relativity. Nobody except a few crackpots. So this was the deflection formula, which comes out from discussing geodesics in the light-like geodesics in the Schwarzschild spacetime. I would like to make a remark which is interesting from a historical point of view. Namely, you can study this problem of light deflection also in a Newtonian context. You just have to assume that photons, particles from which make up light. So you must believe in the model, in the particle model for light. And then you can assume that a light particle gets precisely the same acceleration as any other body according to Newtonian theory. Newtonian theory says that all bodies, all massive bodies, are accelerated by a gravitational field in the same way, if the quotient of inertial mass divided by gravitational mass cancels, if this is a constant. So you might conjecture that also light particles get this acceleration. And then you can calculate what deflection you would get. So you have a light ray which comes in with velocity c. Yeah, that's the value which you measure in the lab for the velocity of light. Then it is accelerated, of course, and it changes its velocity. It will not have the same velocity c during its whole path. It has a c only asymptotically. Then it will go through a minimum value and it will go out again. And you can do precisely the analog of this calculation for the Newtonian case. And actually the first person who did this was Johann von Soldner in 1801, a German astronomer. And the result he got was, well, the exact formula is very much different from the relativistic formula. But if you linearized, you get almost the same thing. The only difference you get is that this factor 2 here is missing. And I suggest that you do this little calculation also in the next worksheet. So this will be a purely Newtonian problem, but I think it's historically quite interesting to see that you can produce the Einstein formula up to the factor 2, also from Newtonian theory, under the assumption that light rays are deflected, get the same acceleration as any other body. For comparison, so Newtonian theory gives delta is approximately Rs over Rm. Well, you may ask, what is Rs in the classical theory? Of course, all these quantities also make sense in Newtonian theory, right? C infinity over Rm. So the C enters the story by the initial velocity, which you give for the light ray. Yeah? You have to prescribe the initial velocity, which the light ray comes from infinity, and that's how the C enters into the formula here. So you get this formula, and this was found by Johann von Soldner in 1801. And the calculation will again be done in worksheet 11. And actually, when Eddington started for his expedition in 1919, the discussion was not just, is there a deflection or is there no deflection? The discussion among physicists was very much, is it the Einstein value or is it the Newton value? So it was important not only to realize that there is a deflection angle, but also that it is a Newtonian value and not that it is the Einsteinian value and not the Newtonian value. And actually, if you look at the data which Eddington collected, it is not so obvious that it is much closer to the Newtonian value than to the Einsteinian value than to the Newtonian value. He cheated a little bit. So there were a few data points which really didn't fit his expectations, and he said, I don't use them where the plate is destroyed. There were ants who were gnawing on this plate, and I ignore this. I don't take this into my measurements. And if he had taken it into the evaluation, actually the value would be much closer, much more shifted towards the Newtonian value than to the Einsteinian value. But that's only of historic relevance. As I told you, nowadays there's no doubt that the Einsteinian theory gives the correct thing. But I think that's an interesting historical fact, and it's not too often mentioned that actually there's also a Newtonian theory of light deflection, and that for some time it was a matter of debate whether this might be the correct theory. So yeah, this was the light deflection formula, which we will further discuss in the worksheets. I would now like to add a remark that you can have much more dramatic situations than this year, where this is a qualitatively interesting but quantitatively tiny effect, right? The deflection angle of an arc second or something like that. So that's nothing dramatic happening. You can have much more dramatic situations if the relation between the diameter of the deflecting body, its mass, and the distance of the observer is different from what it is here. And then you can have even effects like multiple imaging, that gravitational light deflection produces multiple imaging, that you see two images in the sky of only one object, or that an object is strongly distorted, that it is distorted into a ring, for instance. You have a light source behind a deflecting object, and if the alignment is very good, then the object is distorted into a ring, which is called an Einstein ring. So then you have really really dramatic effects. And all these effects go under the name of gravitational lensing. So the theory of gravitational lensing is based on the geodesic equation. So for circular bodies, it is based on the Schwarzschild metric, on the light-like geodesics in Schwarzschild, in the Schwarzschild spacetime. So the theory of light-like geodesics, let me say, is a basis of gravitational lens theory. And you can observe, for instance, multiple images. They have been observed over the last 30 years or so, many of them. So you see several images of a quasar in the sky, and it's actually only one quasar. And you see these so-called Einstein rings. There's also something which is called microlensing. That's an effect on the intensity of a light source. So you can imagine if a light source moves behind a deflecting mass, then at the moment when it is directly behind, or almost directly behind it, then the light is strongly focused towards the observer. Yeah, if the lensing object is very compact, then it has a focusing effect on the light which comes from behind. So the light curve would be something like that if it moves behind the object. Yeah? So it is constant over a long time, then it goes up when the focusing effect is strong, and then it goes down again. And such microlensing events have been observed to a large number, hundreds of them. Most of them were produced by objects in the galactic bulge and in the galactic halo. So these are objects in our own galaxy which acts as a lens here, typically brown dwarfs and things like that. Yeah, very compact and dark objects. So you cannot see them directly. You get only information about them from the gravitational lens effect. So there's also something which is called weak lensing. That's deformation of very distant objects, galaxies typically, and from the way in which the distant galaxies are distorted, you get information about the intervening masses, yeah, about the mass between us and these galaxies. So with this method, you can produce density distributions in galaxy clusters and things like that, and there are more of them. So all this, the theory behind this is based on the theory of light-like geodesics. So we have done this here for the simplest case of spherically symmetric metric, the Schwarzschild metric. So this goes under the name of Schwarzschild lensing. Of course, for most lensing situations, you have to consider more complicated metrics where spherical symmetry is distorted. And that's a very interesting and intensive field of research. Actually, this is very close to my heart because I've been working in lensing for many, many years. This is my main field of research. And if some of you is interested in this, then he may come next year to a specialized lecture on this subject. So I'm planning to give a lecture on gravitational lensing in the next term. So here in this course, I will leave it with this quick remark, but it was appropriate to do it in this place because this gives you an idea on the theoretical background on which gravitational lensing is actually based. So everything comes from the geodesic equations, or the equation for light-like geodesics. So this was what I wanted to talk about, the light-like geodesics in Schwarzschild spacetime. Now time is already over. So I will begin with a time-like case next Wednesday. So then we will discuss, in particular, the perihelion precession of Mercury, which was one of the other great success of general relativity that was able to explain this. And then we will discuss what happens if the body becomes smaller than RS. So then we will talk about black holes. So that's the subject for the next week. And then in the last part of the lecture, I will talk about gravitational waves. So that's the program for the rest of the semester. Have a nice weekend.